One of the most interesting things about mathematical physics is how seemingly complex or chaotic behavior can be describable using models that are in some way tractable by our minds. In quantum systems, for example, we often see behavior which is completely at odds with our common sense understanding about particles such as atoms and electrons, and their behavior in certain materials or in certain phases of matter. Some examples of these purely quantum systems can give real challenges to our understanding, almost to the point that we can ask ourselves, is what we are witnessing really physics at all? Such systems include Bose-Einstein condensates, where we can see individual atoms coalesce into a state where they behave as if they were one single particle, creating quantum macroscopic effects normally seen only at very small scales. Other systems include the effect of quantum entanglement, where individual particles can seemingly interact with each other in non-local behavior without having to worry about the classical restrictions of time and space. One effect which is visually fascinating are the physical properties of superconductors, where we can witness the strange consequences of a phase transition that arises in certain materials where conduction electrons join together to form single quasi-particles and interact with each other using exchanges only describable by quantum mechanics, with the consequences being strange and unclassical descriptions of resistance and magnetism in materials. These seemingly unrelated and hard to grasp phenomena, however, can be made tractable using a combination of mathematical models with analogies to more classical theories of motion and exchange of certain variables. In quantum and classical systems, momentum is the core variable that seems to link the two concepts together mathematically. All systems, classical, quantum, and even relativistic, must conserve momentum. However, some of the ways in which momentum is characterized in these separate fields means that a kind of translation is necessary. Momentum in classical mechanics and relativity is described as a vector quantity, but in quantum mechanics it is also describable as a mathematical operator, which are represented in notation for their application in calculations, normally involving wave functions and matrices. Exchange of momentum in quantum mechanics can be represented in different coordinate systems, and one interesting way to represent the angular momentum of a particle is by using a phase space coordinate system. This is usually accomplished by means of Fourier transform of the particle from position space to momentum phase space. Quantities such as the charge of the particle in a field, such as an electric field, can be described in terms of the particle's angular momentum. In this way, seemingly arbitrary and unrelated labels of particle dynamics, such as its charge, spin, and so on, can be represented as momentum in phase space. A more subtle way to understand quantum mechanics is to realize that the dynamic behavior of particles in quantum mechanics is a complex adaptive system. What do I mean by this? Quantum mechanics, as we discussed, can be based on rules of momentum exchange between particles. These rules are precise. However, within quantum mechanics is a description of the particle as a wave function of its probabilities, not only its probabilities of position, but probabilities of momentum. This is true in real position space or phase momentum space. Therefore, we can see an interplay, a balance, between the exploitation of our momentum exchange rules and the probabilistic dynamics of the system. This creates a system which is complex, but also adaptive, analogous to the problem of gradient descent with a randomly varying term added to it. This leads us to our original proposition, how to represent quantum behavior in which our classical minds can understand. One way is to create mathematical relations between this complex adaptive behavior and classical interpretations of momentum exchange. Newton's cradle offers the archetypal model for momentum exchange in classical mechanics. It turns out that by representing complex adaptive systems in terms of the path integral formalism of quantum field theory, we can create a model with the properties of metaheuristic synchronization in quantum-like networks that can be further formalized into a kind of quantum Newton's cradle. What is more interesting still is the fact that some of the mathematics used here also makes certain summation rules associated with braid networks more describable in terms of quantum mechanics. It's interesting to note that the quantum Newton's cradle has been used extensively in recent years in the description of Bose-Einstein condensates and their behavior of momentum exchange in the laboratory. An underlying structure between these seemingly different phenomena can be made using mathematical physics. With a bit of imagination tied with visual demonstration, we can try to make certain recalcitrant aspects of quantum behavior and complex adaptive systems in general much more easier to understand. Moreover, we can begin to see that many of the systems in nature that we see as too complicated or chaotic to make sensible predictions are nevertheless not without structure and emerge from an interplay of rules and their dynamics that we can describe.